part 4, we talked about single predictor variables. That's what you told me you understand. We've talked about like how we fit the models by minimizing the mean squared error. We also talked about the intuition for what the sampling distribution of the slope parameters tells us. You walked through, you told me exactly like what a p-value means and how to make interpretations about the intercepts. We did this primarily in 2 ways, but sort of 3. We did a numerical predictor variable, and then we also used a categorical, binary categorical variable coded as 0 and 1 as a predictor variable. What we're doing in part 5 is going one step further. What if we have more than one predictor variable? And how does this help us? So to motivate this, I have a couple of questions for you. I have 2 hospitals. This is fake data. I have 2 hospitals. There's a particular condition, and I have 6 survival rates for people with this condition, this hypothetical condition, at both hospitals. So I have a sample of 1,000 at both hospitals. I have the number that survived, and then I have a survival rate. If you were picking between these 2 hospitals, which one would you choose? Hands up for A, commit. Hands up for B, hands up for I don't know. The correct answer will turn out to be I don't know, as you can probably guess. So, I mean, when I look at this, I think hospital A, right? Survival rate is higher than survival rate at B. But it turns out this isn't the whole story, as you can probably expect by me presenting to you very easy questions. So what I've done here is I've broken out the survival rate by severity. So here I have, I have hospital A. I have severity for each, we have 2 different cases, so we have mild and severe. And then I have the number of patients in each hospital with each level of severity. And then I have the number that survived. So I broke out the survival rate by severity across the 2 different hospitals. So which hospital is better? Or where would you go? Hands up for A. Hands up for B. Someone explain to me what just happened. Hospital A, on average, has a higher survival rate. But when we break it out by category, Hospital B has the higher survival rate by category. Yeah.
I was going to say that.
So Anthony was going to say exactly what I just said. How is this possible?
Is it like the proportion is, it would be like, there's a way bigger sample A?
Okay, so something about proportions. Yeah.
Where I was going to say, A had more mild cases than B.
So what if there were different rates of mild and severe by group? Severe cases have a lower survival rate, and mild cases have a higher survival rate. So if there were more mild cases at hospital A, then that would skew the average survival rate higher in group A, even though hospital B was better in each of the categories. And that's exactly it, which I think was similar to both. Yeah, I'm not giving either of you points because they were both great answers. So this is just a picture. I told you to basically never use pie charts. This is one of those cases where I think a pie chart is appropriate. We're looking at percentages. Hospital A 80% of their cases are mild and 20% are severe. And if mild cases have a higher survival rate, then that can skew the average survival rate at Hospital A. Hospital B could look worse simply because they have more severe cases. So what does this tell us? Well, when we think about rates like this, we have to be careful to think about whether there are other factors that contribute. In this case, the actual breakdown of severity by hospital can impact that top line number. This is such a well-known phenomenon. We actually have a term for it. This is called Simpson's paradox. Anyone heard of Simpson's paradox before? Nice, love it, love that. This is something we have to be careful with when we're setting up studies. We have to make the comparison groups appropriate. Okay, so this is just a bit of what happened here, but the main idea is that we have a confounding variable. There's this other factor that impacts that's related to both hospital and survival rate, and that's the severity. So we need to, when we're setting up our studies, we have to think about these other confounding factors. Okay, nice. First off, when you see aggregate summaries, you should be very skeptical. Like, simply top-line numbers are, for this reason, can be misleading. I could easily, I mean, like, what, 95% of you said Hospital A was the one you would go to? It's so easy to mislead people this way. So be careful. And then we have hidden variables, which we're going to think about using control variables for some of these kinds of relationships. Okay. Is this going to keep you up at night like it does for me? I don't usually get scared, but I watched a scary show this weekend, and I was like making food late at night in my kitchen and like had to close the basement door. Okay, so this is what we're doing in part 5. We're thinking about adding control variables to our models. The example we're going to walk through the rest of class today isn't an example of Simpson's paradox. I use Simpson's paradox to illustrate why we care about control variables. But as I'm going to show you, we don't necessarily run into Simpson's paradox every time we need control variables. Okay, any questions? So this is a real banger. We're actually getting our hands on census record data, and we're going to actually perform some estimations. So I have data on from the census records, and we're actually going to test for the presence of a gender wage gap. And this is something we can naturally do using the general linear model. We're going to, over the next couple of classes, we're actually going to test this in a couple of different ways, using slightly different variations on the same model. But this is going to be our main question. Is there a gender wage gap? And are the returns to education different between those coded as male and those coded as female in the census? So the first thing we're going to do is just set up a basic gender wage gap. So first thing, we're just going to check whether there are different baseline wages by gender. In the census records, we have a variable called gender. We'll talk about how it's coded, but we're going to use male and female as our two categories. This obviously restricts how we can code gender in the census, but this is how it's actually coded in the records. So this is what we have to use. If you're thinking about the simplest gender wage gap model, one thing you could do is just plot on the vertical axis. You could plot wages. And then, like we've talked about, we can plot two different groups, take a sample, and plot wages by group. If there's a gender wage gap, we would expect it to look something like this. So there would be a difference between groups. And this is something we can actually go in and test for. This is your standard two-sample t-test that we've been performing. So this is like part 4.2. We have a binary predictor variable that we're using on the horizontal axis, and then an outcome variable that we're trying to predict. So this is a basic model. We can try to test for differences between groups. One way we visualize this is with a slope between the two, but we can also think about this as a vertical difference between means. The slope just tells us whether there is a difference. Okay, any questions here? So we can test this. We could test it with a model that looks like this. So we could try to predict wage using a beta 0, which would be, as you've told me on the mini-exam, this would be the average wage for the 0 group, however we code it. Then we have a beta 1, which would be the difference between the 0 group and the 1 group. In this case, the way I've written the model down, this is male. So I would use this as 1 for male and 0 for female. But as you told me on the mini-exam, we could also code this in the reverse order, right? We could code this we could build a model where the indicator variable is female. So we say female is coded as 1 and male is coded as 0. Then the interpretations would be flipped. So beta 0 would be the average for the male group, and then beta 1 would be the difference between the groups. So this is the model. We call these categorical control variables. Sometimes we call them fixed effects. We'll spend some time talking through these things. But you all want to actually get into this? There's no exercise to turn in for today. I figured you've already turned in enough. But let's get our hands on the data. So what you can do is hop over to exercise 5.1, click on the notebook, and we're gonna just jump in. If you actually want to download this data set, I know some of you are interested in working with census records. Every semester I have a couple of groups who actually go out and use census records for their final project. This is part of me showing this to you is I think this is an interesting kind of analysis. Obviously a very important question, and I think it also shows some of the data sets some of you might be interested in working with. Bless you. So I'm just going to run this. I'm going to save a copy and drive. We'll run this. The first thing I'm going to do is just load the data set. So you can take a look at this column sex. I'm going to recode this as this is, to get in the weeds here a little bit, this is 1 for female and 0 for male. This is what the records look like. I'm going to create an indicator variable for male, just to be a little bit more descriptive. It tells us sort of a yes or no question. So when I run this, I import the data as data, and then I create the new variable called male, and then I'm just showing the output. So the first thing we're going to do is just run a fixed effect. We're going to test for the difference between groups. And all we're going to do is try to predict wages using using mail. First thing I'm going to do, let's see. I'm going to look for income total. So this is income total. I also have income log 10. And if you know anything about incomes, we've talked about this throughout the semester, right? Incomes scale exponentially. Like, there are many fewer people with very, very large incomes, and many more people with very small incomes. So we actually might want to use log base 10. You might also notice I have EDU, so this is years of education, which we're going to use in a second. So be thinking about how we might do these things. I also have degree field, so this tells us different categories of degrees. I had a student last semester who used this set of data to estimate the average income by undergraduate degree. There's lots you can do here. Lots of great data, and this is only really scratching the surface. So first model, I just want to write out how I might do this. So let's say, I'm going to say model is equal to SMF. Wow, look at that. This isn't quite right. SMF dot OLS. Let's do, I want to predict income log 10, squiggly. And then I want to use mail as my predictor. And then I'm going to set data as data, and then fit it, and then print the summary. Okay, any questions here? I also have code for this in the slides if you need. Okay, so run this model and turn to your neighbor, try to interpret what this model is telling us. You all have just told me you can read these kinds of figures. So maybe try to interpret what this is telling us to your neighbor. It'll take maybe 2 minutes here. No, 1 minute. We're trying to get outside. All right, so what do we see here? I could ask you to try to answer. Would you want to? Or do you want me to tell you? Trust the professional. So we see a difference between genders. The male group has a coefficient of 0.16 roughly. We have a very small p-value. Our default null hypothesis is that there's no difference. What we're showing here is that it would be very unlikely for us to see this if there was no difference. The most challenging part of interpreting this output is that this is in log base 10. Incomes are in log base 10. So every unit we move on the horizontal axis, we're increasing by some amount, but in log base 10. So what this is telling us is that we've moved by 0.16 log base 10 units. We're going to spend some time thinking about how to interpret log units as the outcome. But this is part of the trickiness of log, especially log base 10. It actually becomes somewhat challenging. But this is what we're going to work with today. Any questions here? Okay, so great. So this is our first model, but this is not the full story, right? Here we were just trying to test for the, and when I say great, I don't mean I like that result. But for us to, like, observation of social problems is the first place to start. We can look in the data to observe them, and that allows us to think about how to address the problems. This is the first model. The second model you might be interested in is whether there are different returns to education by gender. So what we're going to do is add education as a control variable. So here I have a figure. Unfortunately, no vertical axis. The horizontal axis is years of education. This is just a simulated picture to show an underlying relationship, but this isn't the census records data. The vertical axis we're going to use for wages. But the general trend, we're going to observe this in the census records. The more years of education you have, the higher your income. And we can actually estimate the returns to your education by year. So how valuable is an extra year of education? Which I think for every one of us in this room, this is like an important question to be asked. So that's the first thing we're going to do. So let's go back to the records. And actually for interpretation, I think what I want to do is actually create a natural log income. And Gem and I can write this, but also we can. So let's say income natural log. And then I'm just going to say np.log, and then I'm going to put in income. And what this does is it creates a natural log variable instead of a log base 10. So this is log base E. And then I'm actually going to rerun this. This is a little bit easier to interpret. This is telling us roughly that that the gender wage gap observed just observationally in the census records, there's a 13% wage gap, which I think is a little higher than the more controlled estimate we have in the present. So this might reflect like differences between like older records. So, but this is just the observed gender wage gap in the records, about a 37% difference. Okay, so the next thing is I want to run two different models. The first one is I just want to try to predict earnings across the board using income. So I want to see what happens, like do people with one extra year of education make more earnings? So the way I'm going to do that, I'm just going to try to predict, this is sort of an intermediate step. I want to try to predict log earnings using years of education. And then I have this variable called edu, which is years of education. So if I run this model, this is going to tell me the increase in earnings coming from every additional year of education. Any questions here? I see questions. That's right, yeah, I just did this live. Just np.log, and then put in the incomes total. Okay, any questions here? All right, so turn to someone next to you and try to interpret this number. Yes, the coefficient on education. What's that telling us? Yeah. Okay, someone tell me what this is telling us? Or actually, you want me to answer. This is telling us that every additional year of education adds about 22%. I'm saying this in causal language. This is not causal. This is saying people who go to college for one extra year tend to make roughly 22% more. But this could be for lots of reasons. If you come from a wealthier background, you tend to go to college more, and you tend to make more simply because your parents were wealthier. Lots of other reasons. But this is, roughly 22% more for every additional year of education, which is significant. Okay, so on average, you're doing your job or something. Okay, any questions here? So this is a part 4 story, right? All we've done so far, we've done regressions by category, so binary predictor variable. We've just done numerical predictor variable. But one question you might have is, in the data, it could be that there's a difference in who goes to college. So is there a difference in years of education by gender? This is a question we could ask. So just like Simpson's paradox, one concern we might have is that these factors are all kind of related to each other. Maybe once we compare within genders, the wage, the returns to education might be different, or looking or the returns to education may contribute to the gender wage gap directly. So we could go in either direction. So what we're going to do is actually build a statistical model to test whether the gender wage gap persists after controlling for returns to education. So the way we do this, so the first thing you can realize is this figure can actually be broken into 2 groups. And then all we need to do is, like we did in part 2, we can draw lines through the 2 separate categories separately. So in part 2, we developed scatter plots with separate lines of best fit. This was the last thing we covered in part 2. All we need to do here is develop a statistical model to do that. So let me just talk you through what this picture is showing. We're going to write down the equation, and then we're going to actually test this today. The first thing is we want a baseline intercept term. So all we need is like a base wage for the 0 group. In this case, I'm going to continue to code male as 1 and female as 0. You could flip that and the interpretation would just be different. So my baseline intercept is going to be 0. Then I'm going to add a slope. I'm going to say, I want there to be a slope predicting the returns to education, the income returns to education. But then I also want a separate intercept term specifically for the male group, or the 1 group in this case. So then I have a separate intercept term that separates the 2 groups. So we have parallel lines going through the two categories, but then 2 separate intercepts. We're going to do something different with this kind of model next class, but this is going to be our first foray into more than 1 predictor variable. This is an equation that will do that for you. And let me just talk you through each one of these parts. We're trying to predict wages. We have a baseline intercept, which is the intercept for the 0 group. Then we have a relationship, a predictor variable for education. So we're predicting wages using education. So our beta 1 is just education in this case. It gives us a slope through the data. But then specifically, we also want to separate the groups on the vertical axis by giving them different intercept terms. So it's sort of like we're combining part 4.1 with 4.2. We're including both separate intercepts and a numerical predictor variable. So our wage gap on the vertical axis is given to us by this. So beta 2 is now our wage gap. Any questions here? We can test this. We're going to take it directly to the data and we'll test this. So this is my model. I'm going to switch this from log base 10 to log base to natural log. But we can, this is just one small extra step. Speaking of going to the moon. Okay, my jokes are lost on you. You know, we just launched to the moon like yesterday.
I thought I saw this on Instagram story.
Yeah, this is the first time we're going back to the moon in 50 years, y'all.
They're actually going all the way?
Yes, they're not landing,
Oh,
but they're orbiting.
okay.
Yeah,
The next one's going to be.
we're not orbiting, but
I'm not even doing a full
yeah, we're going all the way around.
Yeah, we're like slowly across the earth and then out.
It's amazing. That's not economics. Let's run a regression. Okay, so I'm going to try to predict log income using education, but I'm also going to try to predict it using our binary predictor variable, male. So I'm going to run this, and it's going to tell us something. Should I run this, or should you run this? I'm going to run this. But you're going to interpret this for someone next to you. We'll spend 2 minutes, and then I'm going to like breeze through the rest of the slides and kick you out. 2 minutes here.
I think like education has one, but like male one.
I mean,
All right. Should I interpret this for you? So I'm going to interpret this for you. If you're still interpreting, that's great. Maybe check the words you were saying against the words I'm saying, just to check whether you're understanding this. The first thing is the intercept. This is just the average log wages for the zero group, which in this case is female. In this case, I mean, log wages are kind of hard to interpret here. The next thing is education, so the returns to education by year. It's about the same, so it's not a fundamentally different number than what we ran up here. It might be slightly larger. That difference can pay off. Like that's a meaningful difference over the course of an educational lifetime. But then the big one is this. This tells us the estimate for the difference in earnings, wages, total income by year, once we've controlled for differences between education. So we're saying we're going to compare two people with the same levels of education and look at the difference in their incomes. And here we can see this number is meaningfully larger than the estimate from before, Claire.
When you just said there are two people's education, are you saying two males and
Male and female with the same amount of education,
that's the
and this is the difference. Yeah. So going back to our picture, what this is telling us is the vertical distance between two people at the same point on the horizontal axis. The beta 2, in this case, is our wage gap, which we estimated to be 0.44, which is roughly 45% difference in the census records. Any questions here? This one?
Yeah, so that's the
This is the difference in the vertical axis, comparing two people with the same level of education. It's the beta 2.
real wage gap.
It's, yeah, once we compare one male to one female, and that difference is 44%. With two people coded different genders and same level of education, they have a difference in 44%. Does that work?
Which
It doesn't need to. Yeah, go ahead.
sure you're saying, I mean, you were saying like males are making more than females, but if this was another like example, how do you know this is very or like X, Y, so on and so forth.
Is your question, how do we construct this model? Yeah, let's spend a second. Maybe we'll chat about this after class. It's a great question. It's not a bad one. I think people want to get outside. So, can I give you like some final slides here? We'll talk a lot more about how to construct these things. But this is what we've just done is look at tests for differences. We've talked about using parallel lines but different intercepts by group. Next time, we're going to look at how we construct differences in the slope itself. Go be outside. Congrats. Give yourself a treat. There's more coffee if you want it.